Okay, so we are back. The next PasswordsCon track is ready to start. So we'd like to welcome everybody to this track. A reminder about our sponsors, Diamond sponsors, Prisma Cloud and Vanta, and our gold sponsors, DropZone AI and SimGrip. And them, along with all the other sponsors and volunteers, again, thanking for all the sponsorship and the work and the effort that goes into producing this conference, and PasswordsCon being possible as well. Just a reminder about cell phones, please put them on silent so that we can pay full attention to what will be presented this afternoon. And then also when it comes to photos, so the B-Science Las Vegas photo policies, no photographs of any presenters or content or attendees unless the presenters give permission. So these presenters don't mind if you take photos of them or their content, so you can, but please no photos of any of the attendees in this room or anywhere else. And there's no need to record, it is being recorded for us already. So, hazard analysis of military AI systems using STPA-SEC, a systems theoretic approach to secure and assured autonomy, by Dr. Josh Hargis and Chris Ward. They're now up. Let's see what it's about.
Thank you. Thanks, everyone. So my name is Josh Hargis. So myself and Chris Ward run a small consultancy called Fire Mountain Labs. We do AI and AI security consulting. Something that we've been working on is trying to kind of adapt some of the frameworks that are out there for other purposes to use for AI security and AI safety. My background, we just started this back in April. I was the chief of AI security at Cranium, an AI security company. Before that, MITRE. Before that, Navy research. Been doing AI for almost 2 decades. I'll let Chris do it.
Hey, Chris Ward, welcome. I'm a Navy veteran. That's where I got my start in security. I was like a radar guy, but you can't be in the military and not learn some security. So got out of the Navy, got a degree in electrical engineering. That's where I started thinking about like processes and system analysis. Met up with Josh at a lab called SPAWAR, which is now defunct and called Naval Information Warfare Center. But that's where we started looking into AI security and how to apply this kind of stuff to AI systems.
Cool. All right, so if you haven't noticed yet, this has nothing to do with passwords. So hopefully that's clear to everyone right off the beginning.
If we get to the end, you're like, I know how this connects to passwords. Let's talk about it.
We would love to know. So bluff, so AI systems can fail without actually breaking in kind of traditional ways. So what we're looking at is ways that are a little bit non-traditional. So traditional failure analysis is not sufficient for AI because of this. So STPA-SEC, we'll get into that, identifies hidden and systemic AI risks. And then it also proactively applies controls for safe AI. So quick outline. So we're going to get into the overview of STPA, some of that background. STPA-SEC, so the security kind of extension of that. We'll go through a case study, look at identifying hazards for these case studies, applying controls, and then we'll leave you with some takeaways. And a little bit of time, I hope, at the end for Q&A. If you have any questions while we're going, though, please feel free to interrupt. So STPA is system theoretic process analysis. So software's role in this complex kind of systems is definitely growing. So STPA is really kind of before software, so it's been around for a very long time. These traditional safety methods are kind of outdated for these modern systems. This isn't even including AI, so that's kind of why the SEC one exists. And then STPA offers kind of a unique system level safety analysis that can be applied to systems, extended to AI systems, which is what we're looking at here. And then the other key part of this is that it can identify hazards beyond component failures. So we'll get into what those hazards are and how to define those. So software safety challenges. So accidents can stem from very complex interactions, as I'm sure you know if you're from the software world. Software flaws are systematic, not random. Traditional methods lack that ability to make software safely and analyze it. So, and then formal verification is not really enough to take us to where we need to go for this. And so STPA is what really helps us link system and software safety. So STAMP is another kind of process out there. So it's system theoretic, accident model, and processes. So that's STAMP. STAMP itself views safety as a system control problem. So if you're from a controls background, some of this might look familiar. Accidents result from inadequate controls and interactions. Whereas STPA, a little different. It's hazard analysis from MIT, identifies causal factors behind component failures, and then really the goal is to prevent hazards. That's really the whole purpose of STPA. So some of the key concepts, so it's a hierarchical approach for system analysis. We'll get into some of these terms, but some of the key terms are loss, hazard, unsafe control action, very important part of this that we'll get to later. These unsafe control actions can lead to hazards, and so they're very important to identify and try to mitigate. And then there's 4 types of these unsafe control actions that we've identified within STPA, and that's these 4 here. So control action required for safety is not provided, so they just didn't put it in. An unsafe control action is provided, so it is there, it's known. Safe control action provided too early or too late. And then the last one is safe control action is stopped too soon. So it falls into one of these categories when you build your kind of unsafe control actions for these hazards. And so you figure out how to kind of categorize that. Okay, so kind of wrapping up this section, so benefits and applications. So really focuses on the interactions among the components, identifies missing feedback or decisions, proactive risk development or risk management in development. So that's one of the key aspects of this is proactive versus after the fact. Versatile across diverse software intensive systems, including AI. So obviously it has to kind of be extended to AI, but the whole point of this is to capture very complex software systems. So some camps out there that just say AI is software, there's some truth to that. So we're extending some of this work for capturing that. And then there is an open source handbook and tool support available out there. There's a ton of literature kind of on this topic. So moving into overview of STPA sec. So this is that extension from STPA into security. So again, we're noticing the software's increasing role into new safety challenges. Kind of a repeat of some of the things, but traditional safety analysis is often insufficient for this new complex software system. Cybersecurity risks are also rising in complex systems. And then finally, STPA sec integrates security into safety analysis. So it's trying to bridge those two things together. So some of the key concepts, we mentioned these earlier. So loss is anything of value to stakeholders. So we'll get into specific ones, but you can imagine this is where you really want to focus your energy. If there's something that you are viable to lose, that is very important to you. STPA sec also expands losses to include security concerns, so not just things of value, but actual, just purely security items. And then a hazard, which we'll talk about some examples, is a system condition leading to a loss. So there's a connection there between hazard and loss. And then finally, the framing, the problem framing defines analysis purpose and context. So these are kind of the main concepts. Now we'll get into some of the scenarios and talk about a little bit more specifically how this applies to kind of AI systems. So there's the UCAs and scenarios. So again, this is that, I already lost my place. So UCAs are the controller's actions that are leading to these hazards. So 4 types, we already covered those types. Focuses on unsecured control actions. And really what we're trying to get at is these scenarios drive how these UCAs arrive. That's really the key part. And then you can translate, some of what we build here into your own systems and systems that you're going to be working on in the future. Accidents stem from these systematic failures and interactions. So some of the benefits and uses. So it really focuses on these complex interactions. We've kind of talked about that. It's proactive for the development side. Broad applicability across diverse systems. We talk about this open source handbook that's also available. So STBA Sec is also well developed, well known out there, and now we'll kind of talk about how you bridge that piece into these AI systems. So case study, we'll dig into a little bit more detail here for AI decision support systems. We've got two that we'll go into. So challenges of AI systems. I'm sure everybody in the room is really starting to think about what these challenges are. It's not magic. It's not going to solve all of our problems. It is very powerful, but what are the things that we need to be concerned with? What are the things we need to start analyzing from a security perspective? So modern systems are increasingly software intensive and complex. Clearly, traditional safety analysis again in the AI space falls short. And then there's new emergent behaviors. There's also like hallucinations. There's all sorts of things that are new from this AI space that are a little different from kind of your traditional software security behaviors. And then our focus here on these case studies is this AI decision support system.
So Josh had a really good point there. We're really thinking about emergent behavior. So this is a planning tool. And it's focused on the mission and business level, not component level failures. So if a hard drive goes bad, what happens to the AI? We're not thinking about that here. We're not thinking about like an AI system necessarily that has levers like training a model, right? We're thinking about what happens when you take an AI model and you put it out in the world with in the wild where there's other objects, people, weather, environmental conditions interacting with either this autonomous system or artificial intelligence agent. So that's where STPA really thrives, is looking at these emergent and complex interactions, which is perfect for AI. It's totally living at this mission business level, right? We have mission objectives. Let's see if an AI can handle it. We fire up some ChatGPT, throw all our documents in it, and something good maybe comes out. That's as coupled as you can get to mission business level with the technology. So it's very important that we do analysis like this. If you look at technical readiness levels, which is maybe an arcane topic, but it goes from like a transition level 1 to 9. And then you do different kinds of testing all the way up at the ladder. So lower levels of the ladder, you're doing lab testing, and then you take a operational capability out in the world, you need to do operational testing. So STPA is a way to do that. It's a way to project. And then we can also talk about how you might use it for red teaming and blue teaming.
So quick thing I'll add is that an interesting aspect of AI that's kind of new for some of these systems that are out there, especially at the operational kind of mission level, is that humans are going to start relying on AI to augment their role. So it's kind of like a human plus technology, which is a little different from the way we've kind of analyzed systems in the past. So having some sort of methodology like this that helps us do that analysis is really important.
Good segue. Like, how many of you have seen this disclaimer like really, really recently? It's in everything that has an AI prompt, right? In the DoD, you don't get to have bad days. You don't get to have an AI decision model like give you bad recommendations and then an operator acts on those. So control actions here, right? I wanted to find an image that really like told the story of control actions. So you have a human operator, you have some kind of autonomous bird in the sky that's taking these footage. That's a controller. And then if you add AI into the mix, maybe an AI model is making a recommendation to this controller. This controller may not trust it and may not take action. That could lead to a loss. So that makes it an unsafe control action. The operator could take the wrong action and you could have a greater loss. You could have a loss of life, loss of a military asset, loss of military secrets. Those are huge compromises that aren't acceptable in a DoD mission space.
Okay, so we've got a couple case studies we'll go through. We'll kind of show the system diagram modeling of what this looks like from a high level. I'll go into some of the hazards, some of the use cases. So this first one here is about an AI coding system. So seemingly something you would want if you're a software engineer, you want some augmentation of your workflow. So clearly LLMs are going to be a very critical part of something like that in an AI system. So we want to automate, kind of the goal here is really automate repetitive coding tasks, generate code snippets. There's all sorts of other things you could imagine you'd want to do with this AI coding system, but that's a clear benefit there. You might also see proactive bug and vulnerability detection. Some of you might be cringing at the fact that that's probably not true, but it is a thing that you could imagine being able to do versus having an engineer, just sit there at the terminal and type Python. You might be able to introduce some of these things. So bunch of system losses you can think about here. One of them is just inoperable or buggy code.
Who's doing like vibe coding type stuff or real coding with AI? Okay.
Scaffolding.
Just
Good.
one? Two? Wow.
Okay, we got a couple. All right, half dozen. Anybody sell their vibe coding company for $1 million yet? Okay.
Us either.
So kind of from a high level again, a simple control diagram of this AI coding system. So some of the components here, controller would be developer, another controller would be your agent plugin, IDE, and then you get to kind of where things live in the lower parts where you're doing logging, you're doing some feedback store, and then you're finally kind of doing a training pipeline. And so you might send a prompt to the agent plugin. That's your control. You might get a AI response back. That's the feedback from that agent plugin, kind of and so on. And you see existing code, generated code coming from that agent plugin to the IDE, and so on. So this is kind of how you would start analyzing an AI coding system. Obviously, you could get much more detailed than this, but this is kind of from a high level what you should be considering as a kind of starting blocks. I'll let you do this one.
Okay, so this one's kind of predicated on like a government analyst or a DoD analyst using an LLM to gather open source intel. So LLMs are really fantastic at parsing through data. It's really easy to point them at Google or like a RAG database or something and say, make sense of this for me. Tell me what I need to worry about in this giant pool of open source intelligence. Well, if you've ever used an LLM, they are gaslighting machines and will outright lie to you. Could be a problem for an analyst that needs to do something actionable, right? So immediately we can see kind of losses that can occur. Is that good? Okay. Here's a control loop diagram for such a system. It's exemplary. But what you have is, again, these controllers at various different points. This one has nice color coding. So the blue lines are control signals and the return lines are like sensor signals. If you think about it from terms of like an actuator, you have a position sensor and an actuator. You sense a position, it returns the position. A controller says, I need you to move here. The actuator moves, feedback circle happens, and then when the actuator gets to the sensor's position, it stops. So that's the whole control loop. So that's what all this is modeling. Control signals, feedback loops, and the thing that does the action.
Okay, so kind of summary slide. So why we'd want to apply STPA-Sec for AI systems. So it actually does start to address this emergent behavior, non-failure risks in AI that are a little bit beyond the sort of normal complexities of software. Reveals systemic risks from misaligned recommendations and feedback. We saw that in the diagrams. We can explore diverse causal factors in AI system workflows. We can proactively integrate safety and security into the system design by looking at those diagrams, and we'll see next how we dive into hazards. And then also it's applicable across kind of various complex AI-enabled systems. So we just gave 2 case studies. You can kind of go through the same process for sort of any AI system. So identifying hazards. So hazard identification and STPA. So just from a high level back to basics of STPA. So it's vital for complex systems because these hazards are really what you're after. Traditional methods, again, fall short of this for complex systems. STPA is a modern approach that helps us integrate hazards and loss into what we're trying to do. And it views it as a control, safety as a control problem. So defining losses. So this all comes back to stakeholder values. So what are the things that the stakeholders actually care about? What are they trying to protect? What are the things that they can't lose? Start by defining what are the unacceptable negative outcomes. You've probably done this in some sort of risk management type of way before, but this is kind of a different way of thinking about it. So losses, especially for, DoD missions, as Chris was mentioning, that can include harm to life, property, and environment. So could be, really, really large things like that, but it could be things that are just important to your organization. So modern systems add mission and data losses, and then we really want to use this to include the specific security losses. So not only thinking about kind of what the stakeholders value, but also putting in things that are very specific to security. So defining system hazards. So these are conditions that lead to loss. So that's really what the hazard is all about. So you want to start with defining these losses. Hazards exist within the system's control boundary. So you can't really build a hazard for something that's outside of your system. You're trying to focus on what is covered by your system. What can you do something about? Focus on controllable system states for design influence. And then, there's some examples. We're obviously going to continue with the case studies that we had, but they can include security and operational violations in addition to, things that you're trying to protect from a stakeholder perspective. So moving this to AI systems, so we want to establish control structure of the AI system. So we want to model commands, feedback, decisions between humans and the AI. So we saw some examples of that, especially in like the OSINT one, the OSINT, where there's an engineer somewhere in the mix that's a human, and then there's a system, an LLM, so interacting. So that's the scenario that we really want to kind of examine closely. And then we want to identify
The power button.
Is it coming back? All right. Yes? All right. And then we want to identify critical system hazards like inaccurate intelligence. I think we had, kind of an example of that. But what are the really critical hazards? It could go back to some of the losses, but that's really what we're looking at there. And then you want to analyze these UCAs, the unsafe control actions, even from non-failures. So even in a case where it's not a drastic failure, I think the gaslighting is a good example. I think generating incorrect code is one that could be very subtle, might not be seen as a failure. So you want to examine kind of past that. Okay. So let's look at this from that AI coding system perspective. So one system loss that we can consider that we talked about before is this inoperable or buggy code. We might have inaccurate code generation and workflow errors as key hazards. So if we're reliant on the system to provide us with code that we're actually going to use on this real system, then incorrect, inaccurate code is going to be a pretty bad hazard for us. And then AI unpredictability obviously creates this emergent and non-failure risks that are key to this analysis. So the control diagram, we'll revisit that real quick. So we've got the developer, agent plugin, the IDE, all the way down to training pipeline. We kind of see from a high level, what the interactions between these things would be. And now we're going to take a look at what that translates into from a high hazard perspective. So these are not necessarily prioritized, but these are some of the identified hazards. So agent generates incorrect, vulnerable, or malicious code. that the developer unknowingly accepts. Feedback and logging data expose sensitive or proprietary code, obviously one that's very important. Prompt context includes misleading, ambiguous, or incomplete information, degrading the model performance, obviously bad for future versions of that model. Updates, we have cursors specifically, but any sort of AI coding system degrades the functionality, introduces regressions, or misaligns with what the user is actually trying to do. Telemetry collection could fail or is manipulated. And then the training pipeline might retrain on biased or low quality feedback data from the process that you're actually instantiating. So all realistic hazards that need to be kind of enumerated to understand how to protect against these.
Sure. So I actually want to go back a slide because there's a really interesting attack that just came out. So if we added GitHub on here, which these kind of tools have access to GitHub now, they can pull repos, they can make commits, they can clone repos. There's an attack vector where README in a Git repository has an adversarial prompt. And so if you tell your AI coding app to pull that repo, clone it, you've now essentially jailbroken your AI coding assistant, and now you don't know what it's doing. So it could be passing API tokens, sensitive information, making unauthorized commits, super fun stuff. So what that would look like is probably another controller that says GitHub hooked onto this IDE, and then ingest the repo, adds it into your code base. So without that extra box, you can't really do the analysis like Josh was saying, so we'd have to add that on. That becomes an extension of our system. So it's very important to capture that because that shows you parts of your attack surface that are available to the adversary. I don't want to spend too much time on this Ascent LLM, but you also need to, we don't even have the control loop here. So you would need to go back to the control loop, and that's how you start building out hazards. And then the next step, which Josh is going to talk about, is start identifying the unsafe control actions that are going to lead to those hazards. So these could be because of accidental operation in the environment. It could be unsafe control actions induced by an adversary to lead to a loss. Or it might be just something that you're considering, like how do we put a control on this and how do we safeguard it so adversary can't come in and tamper with this control.
Yeah, I think some of these are self-explanatory. You can see, one loss might be the inability to categorize data accurately, which, when the analyst is actually relying on that information, that may not be, something that you want to happen. So there's going to be lots of different hazards that kind of come out of that system. So modeling control structure. So we want to look at this from a hierarchical point of view. Try to understand the system components and their interactions, define these control actions and feedback loops, and then we really want to model these AI components explicitly as controllers. And so we've seen that in the past couple slides, where these AI pieces do actually control things. They actually have functionality beyond just receiving signals. So identifying unsafe control actions. So we've gone over those 4 types before, but we really want to define these clearly for the systems that we're talking about here and for those hazards. And we want to do that beyond the component failures, as that slide Chris showed a while back. We're not just operating at the component level. We're not just operating at the system level. We're at kind of the mission operational level. So for the AI coding system, kind of related back to those hazards, so we have some identified ones here. So we have a control action and then an unsafe when something is done. So developer accepts AI-generated code. That could be fine, but it's unsafe without proper review, leading to the deployment of insecure or incorrect logic. So makes sense. But you kind of go down and you enumerate these. So we have, for example, we have a suggestion being returned. That could be fine, but if it's based on undated or irrelevant info, then that might not be what you want. All the way down to things like developer feedback, as applied to training, could be great, but if you're not auditing that feedback, if you're not controlling who has access to give that feedback to the model, then it could be incorrect feedback. It could be feedback that ends up in bias in the training data, et cetera. So these are all potential unsafe control actions based on some of the hazards that we identified, but you can see that as you kind of blow this up and start to build out the system diagram to really control, use everything that's in your system as a control point and kind of feedback. Similarly for the OSINT, we have some non-failure that leads to an inaccurate intelligence. We've gone through some examples of that where you might get inaccurate intelligence or completely hallucinated intelligence. May not be a failure in a usual sense, but that might lead to a failure down the way. We might actually see a situation where we're missing feedback. That causes a misalignment between the model outputs. And we're really trying to do this in a proactive way so that we can identify these risks as soon as we can. Okay, so the loss causal scenarios. So we want to identify what these causal factors are for unsafe control actions. So we're not just kind of identifying hazards, identifying these UCAs, and then calling it good. We actually want to know what are the causal factors. How do you go from one thing to the next? So inadequate control algorithms can also lead to UCAs. Inconsistent process models, definitely that can be a significant factor. So you want to make sure those are correct and detailed. Missing feedback or incorrect inputs can also cause these issues. Specifically to AI LLMs, insufficient training data can impact that. So that could be insufficient from a collection point of view, specific to what you're trying to do. It could just be training data as a whole insufficiency. And then lack of confidence really affects this intelligence workflow. So if you can't trust the data that's coming to you, then obviously that's going to have a big impact on how you do your workflow. So STPA for AI. So some of the benefits, so it addresses AI's unique and emergent hazards, provides comprehensive causal analysis, enables proactive design and integration of safety, applicable across diverse complex AI systems. By extending it all the way to AI, we can do this. And then it also integrates with various safety and security standards. You can bring in now, what is NIST AI RMF say? Like what do we have to think about when we're designing these systems? Secure by design, a great tool to use in hand with something like this. Okay, so we're now at the place where we're going to be applying controls based on these UCAs. So, yeah. So we're going to transition from this hazard identification to risk mitigation. So we've identified the hazards. We're happy with the things that we've built there, but now we want to try to mitigate against those. So we want to apply controls to prevent these occurrences. So we want to integrate safety and security into the engineering process. So feed this back to the engineering team, and then we want to develop inherently safe and secure systems as close to the left as we can possibly get. So core principles, so we want to enforce constraints. So safety is a control problem, not just component failures. Accidents result from inadequate control or unenforced constraints. Controls enforce these constraints, preventing the hazardous states. And then safety constraints are critical boundaries for the system behavior. So you want to have some sort of constraints within the system of how you're going to do this analysis. So deriving requirements. So now we have these unsafe actions. We have these things enumerated. We want to derive requirements. What does our system need to do in order to keep itself safe from these actions? So we want to formalize the safety and security constraints. Those are the constraints from the last slide. We want to create those boundaries. We want to guide system design and implementation based on this information. And then we want to prevent hazards through these concrete requirements. And then formalizing the requirements. We want to formalize any sort of informal safety requirements that we have. Use formal methods like LTL for verification. That's for another talk. But then ensure rigorous software safety verification. So any place that we have these hazards identified, where can we do something to ensure that we're doing the right things from a safety and security perspective in those hazards? And then we want to bridge the gap to formal verification approaches. So we don't have to just end here. We can actually move what we've done analysis-wise into formal verification. And then safe behavior modeling. So we want to model this software behavior for safety. So we can construct with designers and analysts. We can do this collaboratively. We can focus on safety-related variables. We can visualize using UML, other types of state chart notification, state machines, however you want to do it. And then we incorporate these STPA-derived safety requirements back into the full plan. And we've done this kind of thing with people, even in kind of a tabletop exercise kind of point of view. So even something as informal as that can really inform a lot of what this is doing. So generating safety test cases. So we can automate this. We can do this generation from an automated point of view. We can convert the model into testing tool input language. We can do suitability test coverage, generate test data, remove duplicative tests, all sorts of things in order to generate these test cases. I might add, we can use AI to do this. As long as we're doing this in a safely and secure manner, we can utilize AI for this. Software verification and execution. So we can verify the safe behavior model against those STPA requirements that we've formed. We can assure that the model satisfies all of that safety criteria that we've set. Convert abstract test cases into executable scripts. So now we're moving over into the actionable side of this. Run the scripts to validate software implementation, and then link those test cases that we've built back to the requirements for traceability. So fun little image, but one thing you can do with STPA-SEC that's kind of building up to this is that wargaming mitigations. So addressing kind of intentional threats from adversaries. So that's kind of going back a few slides, but thinking about security as really one of the hazards, or one of the what you really want to protect from a stakeholder point of view against adversaries. So if there's intentional threats, trying to model those. Wargaming is a great mitigation tactic for that. You can involve your red and blue teams to build this from a kind of simulated, emulated point of view. And then you assess the effects and costs of those countermeasures. And then you're going to bring what you learned from that back into your system design and analysis. System level interventions. So I'm running a little low on time, so I might run through this. So we want to address hazards beyond the component failures, feedback paths. Really what we're getting to at the bottom here is we want clear accountability for any harms that might come to this system or to the users of the system. And then, as always, continuous improvement and integration. So we want to iterate this throughout the entire system lifecycle, not just at the beginning, not just in the middle, not just at the end. You want to continue to do this. Refine safety and security measures continuously. We want to integrate with software and engineering standards and with those teams, and support. Future work involves tool support and automation. So as this gets more adapted into the AI space, you can expect to see more tools being developed in this space.
So a place where AI is definitely helping in STPA analysis is just enumerating and coming up with hazards that could cause an unsafe control action. That's usually a stage where you need like a few humans in a room, like smashing their head, getting really creative. AI really helps you kind of like go through a bunch of plausibles and see if you can get to these actions. And the hallucinatory aspect of it is kind of a benefit in that regard.
Okay. Couple quick slides on takeaways, and then we'll open up for questions. So I think we've beat this over everybody's head, so maybe there's nothing to continue on here. But one is this risk compliance and governance. So sometimes a complicated space that's very different from system design, but still needs to be integrated back into your workflow. You can use this methodology to bring those things in earlier. And so now, early in your system design, you're thinking about risk compliance and governance instead of towards the end. So you can derive detailed safety requirements from these UCAs, so that helps connect back. And then address intentional security threats back to kind of that red teaming piece, and then enhance compliance with these industry standards that are out there. And with that, we'll open it up for questions.
I thought it was interesting the point that you raised where the system's not trustworthy.
I thought it was interesting the point that you raised that if the operator finds the system to be untrustworthy, not only are you then going to have the risks of the system causing damage due to bad logic, but you're going to have the risk of the operator failing to allow the system to actually do its job.
Yep.
So.
Yeah, I can give you a couple concrete examples. The radar system I worked on, it didn't have AI, but it had like automatic gain control, which is very new at the time. And what it was supposed to do is adapt the filter of the radar automatically to filter clutter out. Well, if you turn this on, it sees a lot of clutter, so it lowers the gain all the way to the bottom. Nice, clean screen, but you're not going to detect an inbound missile with a radar cross-section like smaller than a bee because your filter's so high. We would just turn it off and not use it, so it didn't save us any time, and it cost the Navy a whole lot of money. Another system, computer vision, physical security, camera detecting intruders, right? So the DoD sponsor paid us to come in and do an analysis of how could this go wrong. There's a couple of specific adversarial attack vectors that we want to do analysis for. So one was injecting adversarial artifacts into an image stream. Another was creating these adversarial patches that you can like put on a wall, and if the camera sees it, it suppresses object detections. So very effective. We do the analysis. Not only can you suppress detections, but you can actually create so many false positives that the user instantly turns the system off. So you just undermine the entire security system.
When situations like that arose, what did you do to regain trust in the operator once you had repaired or improved the problem?
So for that one, it kind of underscored that these adversarial patches are a huge problem in AI space, and you have to control them somehow. There were no controls for that before. So if your system encountered this in a wild, it's a new novel threat, there's no control mechanism to suppress it or even deal with it. Maybe a human user would see it and be like, that's a weird pattern. I don't know why it's making all these false positives. So now there's controls. You can do training on your model against those patterns. You can detect the patterns, things like that, to like alert an operator. You can say that we have really low confidence in this detection, so maybe like don't use the system right now, things like that.
One thing I'll add to that is that another thing we learned is that the system just wasn't robust enough. It wasn't built to not only not withstand these patches that we built, the adversarial pieces, but once you started to dig into the system itself, you could give it, kind of noisy samples and it would fail miserably. So it came all the way back to like good TE and V&V. So they needed to get back to the drawing board. Any other questions?
We've got time for one more. No. That's all. Thank you very much. Thanks, everyone, for joining.
Thank you.